Right, so we're moving on today into chapter 8. Chapter 8 is about calculations with chemistry and chemical reactions. And what this is going to marry together for us really are two things, two concepts that we have seen, but we haven't put together yet. Balancing equations and mole conversions. Now, the reason we haven't put those two together yet is because we've never asked you to. But what we're going to find is that it's actually not that difficult to put them together. We just need to know how. And so that's what we're going to talk about today. And then on Friday, we're going to talk about an extension of that, getting into something called limiting reactants and yields. So what I want you to think about is when we start to do these calculations with chemical equations, these calculations and this setup is a lot like a recipe. Let's take a simple recipe. We're going to bake brownies. We're going to make cake out of a box. Recipe on the side of the box is real easy. Take this dry ingredients mix, dump it into a bowl, add these other things to it. Mix it up, put it in the oven, out comes a cake. Well, if I were asking you to take that recipe and turn it into a chemical equation, it would look a lot like this. I had the 2 cups of the prepared mix, so that's 2 mix. I had 1 unit of water, so that's 1 water. I had 3 eggs, so that's 3 E. And I had 1/2 of a unit of vegetable oil, so 1/2 VO. And I put that together, out comes my cake. And in this kind of way, I could also start to think about, well, what if I don't have 3 eggs? What if I only have 1? Could I still make a cake? Yeah, I would just have to adjust everything else, right? Well, that's kind of what's going on here with chemical reactions as well. Our balanced chemical equation ultimately tells us what the ratio of ingredients is going to be. So let's move away from a cake. Let's talk about a combustion reaction. Here I have ethylene, C2H4. If I burn ethylene, the products I'm going to get are carbon dioxide and water. The ratio of those reactions is going to be 1 ethylene for 3 oxygens to make 2 carbon dioxides and 2 waters. Now, does this mean that I have to have 1 mole of ethylene in order to run this reaction? No. But if I change that 1 mole into something else, I would need to change all of the other amounts proportional. And so we're going to come back to these kinds of analogies of recipes again and again, because they're really easy to kind of link up and talk about. And if you read the sections in the book, 8.1 and 8.2, I think they gave the example of pancakes. They use pancakes as their kind of go-to for tying this into something. But the idea is the same. It's a recipe. It's a combination of things. So this brings us into our topic for this entire chapter, stoichiometry. Stoichiometry is a really fancy way of saying calculations in chemical reactions. When we do stoichiometry, we are doing calculations to describe how one reactant or one product is related to another numerically. And again, it seems a lot more complicated. You've got a nice big Scrabble word there that you can't even Scrabble because it's got way too many letters. But the essence of it is calculations, numbers. I want to tell something about this reactant through this other reactant. I want to figure out how much product I should expect based off of this amount of reactant. And by the way, we do the same thing with recipes too. I've got a recipe for a dozen cookies. I need to make 4 dozen for my kids' bake sale. I don't do the same thing 4 times over. I multiply all the ingredients by 4. I mix it up that way. I make one large batch that I just have to keep baking and baking and baking. Where do these numbers come from? Well, they're all rooted in the law of conservation of mass. Law of conservation of mass tells us that mass can't be created or destroyed. So what does that mean? Well, it means that the number of grams that I start with on the reactant side have to equal the number of grams I start with on the product side. All that we're going to go through here is how do I take those grams of reactant and turn them into grams of product. And luckily for us, this process involves stuff that we already know how to do. We've already alluded to the fact that moles are kind of involved in here somewhere. And if we're talking about masses and moles, we're going to be talking about molar masses. The other big component is the balanced chemical equation itself. I have to have one. So the question becomes, how do I use that balanced chemical equation properly? And so when it comes to these stoichiometry calculations, there are really only 3 kinds. And 2 of the kinds you already have done. You already know how to do. You look at the last 2 bullet points there. Turning moles into grams, you know how to do that. You multiply by the molar mass. Turning grams into moles, you know how to do that. You divide by the molar mass. The only part that we're unfamiliar with here, because we just haven't done enough with it, is the part where we turn moles of one thing into moles of another thing. For that, we need a balanced chemical equation, which we have some experience with writing. We just have to use it differently than we have before. And again, it comes back to just think about what we already know. Think about that recipe. That recipe tells me the ratio of one thing to another. If I'm going to use 3 eggs, I need to use 1 cup of water. If I use 6 eggs, I'm going to need to use 2 cups of water instead. Balanced chemical equation gives us that same kind of information. So before we get into this guy, I want to get into just some calculations involving that first kind of calculation, the mold-to-mold calculation, the balanced chemical equation calculation. Because if we can get a handle on that, then the rest of this is just review. We're just doing stuff that we've already done before. We're just calling it something a little bit different. So let's take a look at a couple of example problems. My apologies, the Google keeps turning my arrows into boxes here. I don't know why. But here we've got a balanced chemical equation. It's the same balanced chemical equation that we were looking at in the example before. We've got ethylene reacting with 3 oxygen to make 2 carbon dioxide and 2 waters. The question is, how many moles of carbon dioxide are made when 1.8 moles of oxygen react? The way to answer this kind of calculation is to do a conversion using the balanced chemical equation as the anchor point for where the numbers come from. So if I'm starting, I've got 1.8 moles of oxygen, my conversion factor is going to want to take those moles of oxygen and convert them into moles of carbon dioxide because that's what we were being asked for. Now, where do I get the numbers for this conversion? That's where the balanced chemical equation comes in. The coefficients, those numbers in front of each of those chemical formulas, tell us the ratio, tell us the numbers that we need to pull into the conversion to do the calculation properly. So I've got a 3 here for the oxygen, so it's 3 oxygens. I've got a 2 here on carbon dioxide, so it's 2 carbon dioxides. Like with other dimensional analysis problems that we do, moles cancel out. For oxygen, moles of carbon dioxide are remaining. Multiply across the top, divide across the bottom. 1.8 multiplied by 2, divided by 3. And we get 1.2 moles of carbon dioxide. So all that we need to do for the conversion is just take into consideration what is the relationship between the substance that I'm looking at and the substance that I'm interested in. In this case, it was a 3-to-2 relationship. 3 of the oxygen for every 2 of the carbon dioxide. Let's look at another example. This time we have 8.11 moles of the ethylene. And we want to turn it into oxygen. We're going to do the same kind of conversion. Moles of ethylene on the bottom, so that it cancels out. Moles of oxygen on top. Coefficient for ethylene is 1, so I have 1 ethylene, and I've got 3 oxygens, 8.11 multiplied by 3. My calculator says this. How many digits do I need to round it to? 3. Starting with 3 digits, I need to end with 3 digits. So that's my third digit. That's the one I'm rounding off. 24.3 moles of oxygen would be the correct answer. Okay, so this is how you do the mole conversions. Take whatever it is that we're interested in, use the balanced chemical equation, use the coefficients to figure out how to turn it into something else. Any questions with the process? Okay, then you try this. So I've got 2 questions for you. First question, what type of reaction is this? So when you put your answer in the pear deck, identify the reaction type first, then put in a comma, then answer the second question here. How many moles of iron are going to be made by the reaction of 0.79 moles of zinc? Okay, so we're seeing some good things here. All of you that have responded have recognized at the very least that this is a replacement reaction. And you're correct, it is a replacement reaction. But it's not a double replacement reaction. How do you know the difference? You gotta remember, you gotta count the compounds on each side. Single replacement has 1 compound on each side, that's why it's a single replacement. Double replacement has 2 compounds on each side, that's why it's double replacement. So you want to change your answer because you want to feel better about that? I won't tell anybody. Now for the second part. For the second part, most of you are going in the right direction. Some of you need a little bit of guidance. That's okay. We had to have moles of zinc in the bottom here, so it canceled. We had to have moles of iron in here so that we got the conversion. Where do the numbers come from? They come from the balanced chemical equation itself. So 3 for zinc and 2 for iron meant that this was a 2-to-3 ratio. And if you take 7.79 and multiply it by 2/3, you end up with 0.53 moles of iron. Okay, so this is the thing that is probably as new as it gets for this particular chapter. Everything else that we're going to do in this chapter is either an application or just building off of this. So before we move on, any questions, anything that we're getting tripped up on with this calculation? Okay. So here's where this map that I gave you is going to come in handy. When we do mass conversions, usually mass conversions involve multiple steps because it's not just turning moles of an object into grams of that same object, or grams of one object into moles of that same object. It's using the balanced chemical equation to say, hey, that zinc that we were talking about, what if I had 15 grams of that zinc? How much iron would it make? Okay, that's a lot more complex of a question. But we're going to take some steps to help organize ourselves so that it's not as complicated. And we can kind of see the pathway. And so that's what this is all about. This mole map, which again, similar to we used in chapter 6, a mole map for converting between grams and moles, grams and particles of elements and compounds. It's the same idea. It's from the same manufacturer. That's why it looks so similar. But what we're going to end up stitching together is that we can connect any two of the boxes on this map and use dimensional analysis and the calculations that we already know how to do to link them together to solve the problem. The only thing that we were missing was that bridge in the middle that allowed us to go from one substance to another. But now that we know that we can use the balanced chemical equation to do that, it should be a lot easier for us to kind of visualize what that looks like. We just have to do the same kind of calculation that we just did. So let's dive into this. So here's the mole map. Put it on the screen here. Now, one thing that you can do, these branches off to the sides here related to particles, you can cross those off of that map. And the reason why is, while that is a concept that we will cover in Chem 105, it's not one we're going to cover here. Your book doesn't talk about it. None of your course materials talk about it. None of the quizzes have anything to do with it. None of the exams have anything to do with it. So we're not going to worry about it. We'll save that for future Dr. Bruck and your future Chem 105 class. Let him deal with that. So we're really just focusing on the middle of this. And in the middle of this are calculations that we already know how to do. Calculations that we're actually pretty familiar with. Molar mass. And what we just did with mole-to-mole calculations. That's what we're going to focus on. And the way we're going to go through it, example problems. So here we have 13.33 grams of aluminum being burned in excess oxygen. Question is, what mass of aluminum oxide is formed as a result of this reaction? Now, in order to do a question like this, first and foremost, I know that I'm going to need to turn aluminum into aluminum oxide. I can't do that without a balanced chemical equation. I can't do that. So my first task always is to make sure I have a balanced chemical equation first. And then once I have that balanced chemical equation, I can use the mole math here to help me organize my calculations. So I have aluminum reacting with oxygen to make aluminum oxide, Al2O3. Now to balance this equation, I'm going to need to balance out the oxygens because they're kind of wonky here. I've got 3 oxygens here, but only 2 here. Can't turn a 3 into a 2, can't turn a 2 into 3. I'm going to have to turn them into something they have in common. Common multiple between them would be 6. So 6 oxygens means I'm going to have 2 of these. 6 oxygens means I'm going to have 3 of these. Now all that's left is to balance the aluminum. There are 2 times 2, 4 aluminums here. So 4 aluminum would be there. So we've got the equation balanced. How do I take this and use it? So I'm going to teach you a trick that my high school chemistry teacher taught me. And it's to take this idea of the map and pretend like you're overlaying it on the equation itself. Now, what do I mean by that? Well, let's just imagine that the balanced chemical equation is written right here in the middle of that mole map. So just to illustrate that for if you're watching this later. We're going to do it something like that. Grams of aluminum on the bottom. So I'm going to write that in. Going to tighten it up a little bit here so that it's a little bit easier to see once this mole map goes away. 13.33 grams of aluminum. And ultimately, I don't know. I'm trying to find the number of grams of aluminum oxide. Now, if I follow the map here, the map says that I'm going to need to turn this grams into moles of aluminum. I'm going to need to turn the moles of aluminum into moles of aluminum oxide. And then I'm going to need to turn the moles of aluminum oxide into grams. All right, let's get the map out of the way there just to make it a little bit easier to see. So you can kind of see that I've taken this map and superimposed it over that equation. Grams below, moles above, and I can see how to connect the dots. Now it becomes a matter of doing the calculations to actually connect the dots. Now, one of the notes that I made on that previous slide was that when we do this, we want to make sure that we do it in such a way that we're going to do all of the conversions consecutively. We're going to do them one after another after another. We're not going to round off in between. The reason we don't do that is we want to avoid rounding errors. The more times we round, the more error we introduce, the less reliable our result is going to be. So we're going to do these 3 conversions. Each one of these arrows represents the conversion that we have to do. We're going to do these 3 conversions one after the other, all in a row. So my first conversion would be to turn the 13.33 grams of aluminum into moles. Grams of aluminum need to be turned into moles of aluminum. How do I turn grams into moles? What do I need? molar mass. Where do I get molar masses? Periodic table. Thank you, Thomas. So for aluminum, molar mass is 26.98. My grams of aluminum cancel out. I'm at moles of aluminum. So I'm here now. Just for emphasis, I'm going to change color here just so that we can kind of track where we are in the mole map. My next step would be to turn the moles of aluminum into moles of aluminum oxide. This is the thing that we just did. So where do I get the information to turn those into each other? Where do I get my numbers to turn one thing into another? What's this big thing in the middle? The balanced chemical equation. Thank you. So my numbers, 4 for aluminum, 2 for aluminum oxide. That's going to cancel out my moles of aluminum. Last step, I need to turn the moles of aluminum into grams, or excuse me, moles of aluminum oxide into grams. How do I turn moles into grams? Molar mass. Where do I get molar masses? Periodic table. So for aluminum oxide, I would have 2 aluminums. So that would be 2 times 26.98. And I have 3 oxygens, so that would be 3 times 16. Total mass here is 101.96 grams per mole. Moles of aluminum oxide cancel. Now I'm left with just grams of aluminum oxide. So I've got my 3 calculation steps here. Now I just need to do the numbers. Multiply everything in the numerator, divide everything in the denominator. So 13.33 multiplied by 2, multiplied by 101.96, divided by 26.98, and divided by 4. How many digits do I need to have? 4. I'm starting with 4. Every calculation has at least 4 in it, if not more. The only one that doesn't is the mole ratio, but that's an exact conversion. So 4 come out of this, 25.19 grams of aluminum oxide. Any questions so far? All right, let's try another one here. Here I have a reaction between copper 1 oxide, cuprite, and carbon to make purified copper. Question is, how much cuprite do I need to make 256 grams of copper for a bracelet? Process is pretty much exactly the same. We're gonna overlay the mole map here. So I have 256 grams of copper. I'm trying to figure out the number of grams of cuprite. So I need to turn the grams into moles of copper. I need to turn the moles of copper into moles of cuprite. And I need to turn the moles of cuprite into grams of cuprite. Process, again, exactly the same. So this is what I want you to use this map for. This is an organizational tool. Help you to figure out, okay, if I'm here, how do I get to here? Well, map says I need to use molar mass to turn it into moles. Use the equation to turn it into moles of the other thing. Use the molar mass to turn that other thing into grams. So first step, 256 grams of copper. First thing I want to do is turn the grams of copper into moles. For that, I need the molar mass. Molar mass comes from the periodic table. Molar mass for copper, Cu, 63.55. Grams of copper cancel. I've got moles now. So I've climbed the first hurdle. I want to turn moles of copper into moles of cuprite. For that, I want to use the balanced chemical equation. I can see that the ratio there is 4:2. 4 coppers for 2 cuprites. My moles of copper cancel. I can move on to the next step. Last step here, I want to turn the moles of cuprite into grams of cuprite. For that, I need the molar mass again. Molar mass of copper, 63.55, and there are 2 of them, so times 2. Plus oxygen, which is 16. Total mass, 143.10. Moles of cuprite cancel. I'm left with just grams. How many digits in the calculation this time? 3. Starting with 3, every other digit, every other calculation here has more than 3. So I'm going to round to the 3rd digit. So my calculator said 256 times 2 times 143.10 and divided by 63.55 and 4. My calculator gives me a whole bunch here, 288.2265 and so on and so on. Remember, I only need 3. So that 3rd digit is the 8 here. We're going to round it to 288 grams of cuprite. So if we are looking forward here, this is the kind of calculation that you're going to see in the homework assignment due tomorrow night. This is also, if you think about how our quizzes are structured, Friday's quiz is net ionic equations, which we talked about on Monday and the time before spring break, and stoichiometry. So there's going to be 2 net ionic equations. There's going to be a couple of conversions like this, where you have to go from grams of one thing to grams of another thing. So it's really important that if you're struggling with something, to try to get help, try to ask as quickly as possible. So, before I throw up the last question of the day, does anyone have any questions about stoichiometry and kind of the process here? Okay, so on Friday, we're going to be moving on into the next kind of piece of this. And the next piece of this is where we start to look at predicting product. So if I have this reactant and this reactant, how much product is it going to give us? Now, that particular type of problem is a little bit harder because before we can even answer the question of how much product there is, we have to first answer the question, which of the reactants is going to run out first? And so Friday's class is going to be kind of multi-dimensional in that place. I'm going to teach you how to do both things at the same time. How do you identify what runs out first? How do you identify how much product to get at the end? Have a good day.